Ladies and gentlemen, welcome to the Webit.net programming tutorial series on Introduction to Object-Oriented Programming.
Woohoo!
Yeah, so this is a high-level overview of object-oriented programming. So we're not going to go too deep into code. This is just so that you understand the concept, so when we talk about code, you know exactly what we're talking about.
For some reason, programmers sort of divide themselves into two halves. There's people who learn programming like in the early 80s and before, and people who learn programming from the 80s on.
Yep.
And for some reason, a lot of people who learned programming in the 70s sometimes have like a very difficult concept wrapping their head around in object-oriented programming.
Yep.
And even in the universities, a lot of students sometimes will really get just hung up on the object-oriented programming concepts.
Right. And they're not really well explained.
Yeah.
In a lot of schools.
And they're very abstract. So we just wanted to really like focus on the concepts. We're not going to be talking about a lot of coding here, but we're going to just drill in the concepts so you just get like a solid understanding of object-oriented programming.
Right.
It's going to be a lot of fun. Object-oriented programming is very cool.
Exactly. If you don't learn this, you might as well stick a fork in your development career. Because this is it. Now, try to think of this, guys, as like you're watching a cartoon. Like this is a Saturday morning cartoon, really. So don't get too hung up on things. If you gotta watch it over and over again, do it. We have nice fun colors in this presentation, so
but like don't like worry about taking notes and trying to like think of whatever. Just relax. This will be fun.
All right, here we go, Brian. What is object-oriented programming?
In the most basic sense, it's a programming method or a style of programming that is driven on custom data types.
Yes.
So we've kind of seen our own type def before in C, and we've kind of seen like when we define a structure.
Mm-hmm. Or a stupid union.
Right. We kind of make our own data type, but we're really going to explode on that idea.
Oh, yeah.
And really blow it up. So instead of having just a variable like an integer and a char and stuff, we're going to have one called a frog data type. You know? And now the difference though is these custom data types don't just have members.
Yeah.
But they can also have methods.
Yes.
Or functions.
Yes. You know them as functions, but forget that you know the word functions. Because method is now your new word for functions. So here's a formal definition, Brian. It's a programming method of using data structures that contain methods, functions, and fields, attributes.
Right.
So they can be kind of synonymous with a class, which is like C++ and C# and Java uses that terminology. Some programming languages use the term interface, and it means that those two both mean the exact same thing as object. Although one thing to keep in mind, like in C# and in C++, interface actually means something else. But languages that use that terminology, it's synonymous with an object.
Right. So the basic concept is that just like in Aristotle's On the Forms, there was like the concept of a dog and like what the form of a dog is and how it is that whenever we see a dog, we recognize it as a dog.
Right, yeah.
But then there's that dog and there's that dog. So how is it that a dog can be like, dogs are so different. Like you see like a little Shih Tzu and it's all weird looking and fuzzy.
Right.
And then you see like a Great Dane.
Right.
And like they're completely different looking things, but we still understand them as like a dog.
Right, exactly.
So that Aristotle On the Forms, like a frog in this case, we're gonna define out like what is the form of a frog or like the concept of a frog.
Right.
But then we have an instance of a frog. And then we have like another instance of a frog, which is like a different color
different,
frog.
yeah.
And then a different color frog. So we're gonna have the concept of the frog, and then we're gonna have like actual instances of frogs, places.
Right. And depending on how the template of the frog is designed, we could have multiple different types of frogs that come from the exact same object or template of a frog.
Yep. So there's effectively two types of object-oriented languages.
Yep.
So ones that support object-oriented concepts, and one that are pure implementations of object-oriented programming.
Oh, yeah.
So
and they're both very different.
Yeah. So the ones that support object-oriented programming are still procedural languages. They're still top-down, but they have object-oriented components built in or bolted onto them. So this would be like a C++ or Objective-C.
Right.
Objective-C, which is C with objects.
Right. C with classes in object-oriented programming in C.
So then there's also pure object-oriented programming languages that are built natively on this concept where even like the main function is part of an object.
Right, exactly.
Everything is objects. So That would be like Java and C# and languages like that.
How is object-oriented programming similar to concepts that we've already discussed? Well, they're kind of like structures and unions. Kind of. But they're fundamentally different in a few ways. Classes can have their own functions, which we discussed before. They're called methods. Classes can also contain private and or protected data, which we'll talk about more in a few. Classes can also inherit from other classes and absorb their functionality.
It's like an X-Men superhero or
something. Right, yeah.
I will absorb your special skills and use them as my own. Or like Heroes or something.
Right, yeah. Who was the X-Men that could do that?
There's the villain in Heroes. Oh, no. It was a Mystic.
Yeah, the guy. No. It was the cat, Nightcrawler.
Oh, yeah.
Could absorb the powers of other people.
Okay. Anyway.
Now, you can have a structure that has a structure inside of it, but you can't have a structure absorb another structure. And like if there's a bubble floating around, another bubble floating around, and they just kind of combine into one bubble, a class can do that. So each class acts as its own entity, completely separate from the rest of the program, that you can kind of view like a little tiny program that exists inside of the rest of the program.
Right, so now we're going to start almost developing like ecosystems of programs.
Exactly right, yeah.
So it's awesome. It's very cool, just like real life.
So let's compare this to the modularity concept that we've discussed, Brian. In the modularity concept, this is something that we are all familiar with. We have a main function, and then we have other functions that belong to the main function. So the main function can call a function and say, give me a result, and it will get a result. Now, the object-oriented model is a little bit different, Brian. So why don't you tell us how the object-oriented model works?
So in the object-oriented model, one of the objects themselves will contain an entry point.
Right.
Or a main function.
Right.
So this calls another method inside of the object they're both contained in. But not only that, we can have other class definitions of other objects and other object instances where we can call another object and then call a function or a method inside of that other object and then return its value back to where we're executing code from. So this really kind of creates like a whole system and structure of objects that talk to other objects and call methods inside other objects. It's very cool.
And believe it or not, this actually acts more like real life works. Because, Brian, as you and I are sitting here talking, we're interfacing with each other.
Right, we're two different instances of an object.
Right, we're not like, in the modularity model, Brian and I would exist as the same creature. But in the object-oriented model, we are two completely different instances that are interfacing with one another. And that's actually how classes communicate. They communicate by interfacing, which is also called message passing. And that is the act of one object or one instance evoking a method inside of another object.
So it's kind of like the DLL libraries we saw, but not really. It's all sort of being defined all well within our environment. So let's take a look at how objects are composed.
Yep.
So just like in C, our programs have to start somewhere.
Right, exactly.
So in object-oriented programming, you'll have kind of a central object that contains an entry point, and that will be considered to be the main class. So the main class is the class that contains the entry point function, or the main function.
Right.
Not all object-oriented programming languages use the main class concept. Like scripting languages just kind of start where you start the program.
Right. Or Objective-C and C++ don't have the main class concept, but they still conform to the main function concept.
Right.
So the scripting languages are they're called dynamic programming languages because the entry point of the script doesn't follow the same conventions as other programs. But we're not really talking about scripting languages. Just throw that out there.
But generally speaking, we're going to be thinking in terms of having a main class. And then we're also going to be thinking in terms of having a supporting class.
Right.
So, supporting class is all the other objects, object definitions, and the main class is the one that has an entry point, basically.
Right.
So objects are often described as an encapsulation of methods and attributes. We have kind of, you can think of it literally as like a capsule.
Right.
And we put a whole bunch of, methods and attributes into that capsule, and then we encapsulate it.
Boom!
So now we have, we've got this thing that contains a whole bunch of different methods and attributes.
Yeah, now we have multiple encapsulations of methods and attributes. And as Whippet the Frog is telling us here, each one of those is its own ecosystem.
Yep.
Completely independent from one another.
Do you remember in the example we were talking about a person?
Yeah, back in the introduction class, little introduction series.
So we have like a person object, let's say. So this is the potential of a person. It's like the idea of a person. It's the concept.
Right.
But then we can have the instance of a person, like you or me, like the actual person, the entity of a person. So I am a person. I'm from the person concept. I fit to the person concept.
And inside of all these objects and classes, they contain things called members. Now, members can be basically anything that belongs to a class. So we have field definitions, methods, properties, and delegates, all of which we will discuss throughout this programming series, or this tutorial series.
So fields are also known as attributes or properties, but properties we generally won't refer to them as. Yeah. Usually we'll call fields an attribute.
And the reason why is properties are in a lot of OOP languages is a different concept. Now, languages that don't support the properties concept will allow that terminology in its context, but for the most part, Brian and I are going to say that the term properties is incorrect terminology when talking about OOP, but you may hear it.
Yep. And then there's the members of an object that are data types can be like integers and strings and other objects that we define and so on. They also contain methods, and methods are just a function, but the function belongs to that object or to that class. It's defined in that class. So it's a function just like we always define functions. It's just accessible when you access that object. So all functions in object-oriented programming are called methods.
Right.
It's just a way to differentiate saying that something's a function, like in our classic way of understanding it.
Right.
And differentiate it with something that belongs to an object.
Right. Kind of like we have an example here, like if I say I'm going to go to my car, or I'm going to go to my truck, it evokes different mental images. Like, there's a party at my apartment, and there's a party at my house.
Right.
Creates two different mental images. Even though, your house can be your apartment, they both are, the terminology evokes different thoughts. And that's why it's important to use methods and not functions when talking about object-oriented programming. In the modularity concept, the main function has functions, and these functions belong to the main function. Now, in the object-oriented model, the object contains functions, and the functions only belong to the object. So if there's a main class that doesn't own these functions, it has to go through the object or the object instance to get to these functions.
So there's two types of members. There's class-level access, which is static, and instance-level access, non-static. So we have basically two types of members. We have class-level access, which is static, and instance-level access, which is non-static. So basically you have, like we talked about before, we have the concept of a class, the definition of a class, and then we have an actual instance of the class. So we can have a method or a member, I should say, at the concept level or at the instance level. So for example, we can say person dot how many people, which would give us the population, or we can say this person is smelly, true or false.
Right.
So the basic difference is just that you have one that's attached to the class level and one that's attached to the instance level.
Right, because of the population of humans is not a property of Brian or me.
Right.
We are just instances of people, but like Brian was saying, the concept of the person, the object of the person.
Like Kevin is smelly, true.
Yes. But Kevin population number is not.
Right.
Population belongs to my human or my person class. That's where that information comes from.
Yep.
So when we start talking about members, we have three basic access levels. Most OOP languages follow these conventions. So we have public, accessible by any code, anywhere. So if you create an instance of an object or you have access to an object that has a static member, you can access any public member at all. Private is only accessible to the members inside of the object and also other friendly functions, which we'll talk about later. Protected members are accessible to the object in the same way that private members are, but they are inheritable by other objects that they can just use those as if they're objects that belong to itself.
So let's take a look at how objects are composed. Here we have an object type, or a class, and we have public and private members. So the public attributes and the static attributes and the constructors, deconstructors, methods, all that kind of stuff is accessible from outside the object. And so that's accessible to all external code. And then the private members are only accessible to code from within the class.
Right. We don't have protected members here, but we will discuss more in depth when we get into inheritance where those come into play.
In any circumstance, these are all attribute members or instance level access. These attributes here. That's the non-static attribute. If we look over on the right, the static attributes, those are the class level access data types. So those are the data types that we access from the object type concept.
Mm-hmm.
And then the same thing applies with methods being static or non-static. These are the object instance methods. And then these are the class level static. We also in the public functions have a constructor, which is kind of like the initialization function. So the constructor is called when you create an instance. And then we have the destructor, which is when you destroy an instance.
So here on the left, we have the object, which Brian kind of laid out for you. But on the right here, we have these little bubbles that are coming out of the object, and these are all the instances of the object. Now, one thing to keep in mind is we have these little red no or Ghostbuster signs, whatever, over the static members. That's to represent the only members that go with the instances are the non-static members. Static members do not go out with the instances. They stay back with the object type itself. So the instances do not have these values with them at all.
So this kind of gets us up and running. This kind of gets us off the ground with the idea of objects and object-oriented programming.
Yep.
So now that we have the basic concept of form and the idea of an object, and then the actual instance of an object, and the fact that objects can have members that can be like attributes, like variables, and methods that are like functions, and all that kind of stuff, we can now we have that primary foundation to kind of now we jump off of and say, okay, so now that we have that, what do we do with them?
Yep.
And as it turns out, a whole bunch of cool stuff.
And
so
we're going to define that as we go along.
Yep. So thanks for watching.
Hey guys, welcome back to the introduction to OOP. We're going to be talking in this video about the basics of class construction.
Nice.
So
before we were talking about how there's the concept of the frog, or the concept of the dog, and then you have like different kinds of dogs. So in this video, we're really going to talk about like how to actually construct that definition, that abstract definition.
Yes.
So it'll be pretty cool.
So constructing a class, first we have to define the new object type, like the frog or whatever. Then we have to build the parts, or the little pieces, the fields, attributes that make up this new type. And then lastly, we use this template to create an instance of the object that we have just created. So, fundamental question, Brian, and this is a question that people have asked themselves over the ages, and we will definitively answer this question without a shadow of a doubt in this video series. So this is legendary.
It's pretty amazing.
So, the chicken-eggy situation, Brian, what came first, the chicken or the egg?
Let's see here. So we'd have to define an egg, but then the egg can hatch and become a chicken object, but then we could define the chicken object, which could produce an egg, which is the definition of...
So let's see if we can figure this thing out.
This is a little chicken-eggy.
Yeah, this is very chicken-eggy. So, Brian, let's say that you and I are the creators.
The creator
of the universe.
The universe.
We want to make an animal called a chicken.
No, yeah, because we are all powerful, almighty, and what do we want to do with our spare time? We want to create
a chicken.
Chicken. I know it sounds so masterful and devious.
Yeah. So, Brian, explain how you and I, as the creators, can make a chicken happen.
All right. Well, we first define things about the chicken, like it has a head.
Yeah, that's good.
And it has like wings,
and
feet and eyes, and what an eye is, and beak and feathers, but it also has like functionality,
right?
Or like action. So it can walk, it can cluck, it can eat, it can breathe, flap its wings, breed, it can reproduce, it can produce other chickens.
Another instance of a chicken object.
Interesting.
Huh, that's craziness. So, here we go. We then create this template of what we believe a chicken is, and then we make the instances. Now, here's the beauty of all this, Brian, is we're going to drill this in right now. The chicken is the potential, the object, and the actual chicken itself is the entity.
Exactly. Easy.
Done. Yeah. So we have created entities.
Yeah. So now we have like a whole bunch of little chicks running around all over the place.
So now that we've gone through this, Brian, I need the definitive answer to the question, what came first, the chicken or the egg?
First you have the creator.
The creator.
Then the egg.
Yep.
And then in the egg definition was the chicken definition.
Yep. So we have answered the age-old question that philosophers have asked themselves for thousands of years.
Yes, exactly.
In just 10 seconds.
Nice.
And object-oriented programming is what led us to this answer.
Very cool.
It is the only truth that exists. This is yours, Brian.
All truth must be known in object-oriented. Now, it is kind of weird, though, because after you program in an object-oriented way for a while, it does, I'm not saying object-oriented is like some weird mythology or anything, but it does kind of screw with your head.
It turns into the Force from Star Wars.
Yeah, because when I'm walking around and I see somebody like, shopping cart dot, retrieve this, or I see like car dot color is this. Like after a while you start looking at like real world situations.
Yep.
And then you also look at like business models and business structures, and you start seeing that as object-oriented programming.
Right, exactly.
You start seeing as government and things as object-oriented programming.
But see, that's the beauty.
It's very fun. It's very cool.
Once you train your mind to think that way, you become an amazing programmer.
Yeah.
Because then someone comes to you with a problem, and you're like, boom, I got this all written out. We have our object structure like this.
Yep.
The program will flow like this. Done.
It's very cool.
Yeah, so Brian, talk to me here.
So how do you build classes? Well, every language has their own way that they want to build classes. But generally speaking, if it's a pure object-oriented programming language, then a template's not required. Yep. Because you're in it, you're involved in it, they know that's what you're out to do.
It's naturally object-oriented, so why do I have to template anything?
Right. So, but if it's a bolt-on language, then a template's required so that it understands what you're getting at.
Yeah, and typically, objects are constructed using 2 files and executed with a third, which we've sort of seen this already with the DLL programming. Interesting here.
Yeah.
So we have a header file, also known as an interface or a template file, and this basically contains the object template. So what to expect the object to be, sort of.
Yeah.
Then the implementation file is the code that defines the stuff that was declared in the header file or the implementation or the interface file.
Cool.
The driver file is the code file that brings in the implementation file, which in turn brings in the header file, which then creates the object. So now we can actually use the object and create instances of that object.
Yeah, easy.
Yeah, it's awesome. So we have a header file here.
And that has my class,
yep,
which contains my function 1, 2, and 3.
Yep, and now we have an implementation file here.
Which are known as methods.
Yes, yes.
So then on the right, we have our implementation file. So that is the code in the code blocks to actually, really hash out what all the functions do. And these are tied together.
So the two of these together make a class.
Right.
They make an object. So you can see that in our new class here, our little functions are sitting there and they're defined. They can be used. But with these 2 files together, it's useless. It's just the potential to have potential.
Right. So now let's go to our driver file and use it. So then we have our driver program, which calls my class C, just like our variable declarations where we have like int num.
Yep.
It's just now my class C. And so that my class is that thing that we define.
Mm-hmm.
So that is a class of objects. And our object instance is C.
Right.
Beautiful.
So we go out and we say, give me an instance. And now we have an instance.
Very cool.
Yep. So the basics of class construction are pretty simple. We have implementation and a header file that combine to make an object in most languages, and then we have a driver file that makes use of that object.
And now that you know class construction, you can go create your own universe.
Yes.
Universe.
Because the universe is an object, an instance of an object that has other instances of objects inside of it. Oh my goodness. The creator must be a very intelligent and very busy creature.
I know, and he even thought of freaky stuff like davidbowie.leotard.color. I mean, it's awesome.
All right, thanks, guys. See you in the next one. Welcome back. Introduction to object-oriented programming. I am Kevin, and I have
Brian.
In this video, we're going to be talking about abstraction.
Nice.
Now, abstraction is kind of an abstract concept.
It'll blow your mind, man.
Yeah.
It'll just blow your mind.
Insert David Bowie joke here.
Yes.
So, Brian, let's go over the basics. What is abstraction, and what does abstraction have to do with object-oriented programming?
So, what's the difference between a language from the 50s or 60s or 70s and a language today? Well, largely it's abstraction for the sake of readability and usability.
Right.
So if we have a language that can say, as you type the language, it can say something like, I want the computer to do this in like a very natural form.
Mm-hmm.
You're really not saying, I want you to iterate through this loop and move this into the memory piece over here, there, and there.
Right.
You're speaking in very broad strokes, in a very abstract sense.
Mm-hmm.
So abstraction is the ability to start pulling out of the machine code and get further away from machine code until you can really speak and define things in very broad strokes. So that's kind of what we're going to talk about, is how object-oriented programming creates abstraction in programming. So we can essentially say that abstraction is hiding the details of a process from the user. Object-oriented programming code, the programmer should know but does not need to know all the intricate details, just how to use them.
So in this example here, let's take a look at 2 objects, okay? We have a car and we have a car factory. And the car contains all the fields and methods that make up a car, whereas the car factory contains all the fields and methods that are required to make a car. So inside of my car factory, I have a method to build a car. And when this method is complete, it's going to return to me a car. So now I have my little main bubble floating over here, and he wants a car. So he says, build me a car. And the car factory goes out to all of its different members and goes, vroom, vroom, ticka, 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 ding, ding, ding. And at the end, it returns me a car. Now our main bubble has a car. And from our main bubble's perspective, it doesn't care. It just said, give it to me. And the car factory had all of its hidden details and just gave me back exactly what I asked for.
Very cool.
So in the same context, when the main bubble wants to use the car, he just wants to call a method. When I start the car, I don't care how it happens. I turn the key, it happens. When I hit the brake, just stop. You know, when I accelerate, just work. You know, when I turn, just turn. So when I go into my car and I ask, please start, the only thing I want to know is, did you work or did you not work? So that's basically abstraction.
And that way we're really writing on a level of what we want to do, not how to do it.
Precisely.
Very, very fast to develop that way.
Mm-hmm.
So one of the concepts that we're going to see with abstraction and object-oriented programming is this idea of setters and getters.
Mm-hmm.
Setters and getters generally are associated with a property of an object.
Right.
And when you deal with a property, you either set the property or you get the property. So whenever you define a property, you define a set and a get. So whereas if you access a variable in an object, that variable has a value. But if you have a setter and getter, when you go to use that value can be calculated. So a setter and a getter is a method of indirectly setting values within the class.
Mm-hmm.
So instead of just accessing a value, we can actually write code of how you access that value and how you retrieve that value.
Yep, or just typically considered best practice to never allow code to directly access private members.
Absolutely.
So even if it makes no sense, why am I doing this? I have another property that allows you to get and set. It's always better to code that way. Never allow access to private members.
And there's as we'll see later, that you can do a lot of very powerful stuff with setters and getters and validating the input that's being declared into an object's variable. So these are implemented in two ways, through methods and just manually saying, get this value and set this value. Or in properties like we were discussing.
So here's an example of how a setter and getter can be used. So on the right here I have my main code and I have an instance of person, and the person is called me. And inside of this class, the private members are the first name and the last name of this person, and it has two methods. One that allows you to set the first name and get the first name. Now obviously this person can't have a last name change, so whatever he's born with is what he's stuck with.
Right.
So in this case, we're going to say I want to set the first name to Wibbit. So we go to this function and we go to this method and pass Wibbit as the parameter. Now first name equals Wibbit. So on the next line down here or further down in the code, I want to retrieve that value. So I ask this method, get the first name. So the method goes out to the attribute or the field, returns the value, and sends that to the calling code.
And this way, the calling code never has direct access to those private variables. It's always accessing them through the public methods. So here's another example where we have a birth date value that's private, and we have a public member saying get years old.
Right. So in this case, we're not storing how many years old you are.
Right. Because
only your birthday.
Right. Because it's we have a value that's birthday, which doesn't change, but what time it is now does change. So when we call this public method,
we can't directly access this value.
So that's not an option. So when we call this public method, we call get years old. It gets the birth date, it performs a calculation, it returns that value back to the main code of how many years old that person is. Very convenient.
So you might be asking yourself, what is the big deal? I mean, this comes in handy in many ways. Like one really obvious example is having read-only values. I want to have a value that I can retrieve, but I can never set. If you have a field that is public, it can be set and it can be retrieved. You can set the value, you can retrieve from it, even if you don't want that to happen. That,
right.
You're given that functionality.
And if it's private, you can't read it. The other thing that you can do in a bit more complicated of a way is you can write security access into your program, especially for larger applications. And so the way that you bake security access throughout your program can be baked into all of the objects themselves, so that when you get or set an object, it can authenticate security access to those objects. And do you have, or does the calling code have permission or authentication to be able to even set an object's parameter, which is very cool.
So like one really basic example, for those of you that are still on the fence about this, is when you go to the bank. You go to the teller with your little withdrawal slip. I want $50. You give the teller the bank or the ATM machine the slip. Well, they don't say, okay, go into the vault and get it yourself. They do it on your behalf. And that's really the fundamental, a human example of a getter.
Right. Wouldn't that be awesome if the ATM could just open up and you could just reach in and be like, no, seriously, I'm only getting like $100.
Well, because in that case, the money is the private field, and then you interacting with that money is the public method of doing that, which would be the setter and the getter. overloading!
Oh, this is awesome.
I'm overloading with excitement about object-oriented programming.
So method overloading is very cool. It provides multiple methods with a variety of parameters. So if you want to call a method with passing it an integer, and then you want to call it again, passing it a string, it's really the same method.
Yep.
You can just have different types of arguments that you can pass into it.
And based on the input data type, the programming language will know which function to execute.
Mm-hmm. So this helps make methods work in a variety of circumstances. It makes them more generic.
Mm-hmm.
So we can have a function that just generally says, how old are you? And you can pass in a date time, or you can pass in a whatever you want. You can pass in just an integer value.
Right. You can say, I'm 15 years old, or I'm 15.3 years old.
Right.
An integer and the
or
double.
Or this many seconds since.
Right. Yeah.
1970. So in providing a method to set with a number within a class, this will allow multiple outlets. So take this instance, for instance. So we have a number class instance, and we have a private double number.
Mm-hmm.
Then we have some public functions.
Methods.
Methods, sorry.
That was me slapping Brian in the face.
We gotta cut that out. So then we have a series of public methods. So these public methods all have the same method name.
Yep.
Set number, set number, set number. But the difference is one has an argument of an integer, set number float, set number double.
Mm-hmm.
So this way, whatever we pass, if we pass in an integer, if we pass in a float, we can handle each of those circumstances to access the private double.
Mm-hmm.
So if we say set number integer, we're going to have to do a conversion to set that as a double. Whereas we call set number double, if we say set number double, we just store that value. So we would handle that in different circumstances differently.
Okay, Brian, let's talk about method overriding. Now, what is the difference between overloading a function and overriding a function? Well, overloading gives you multiple outlets, whereas overriding basically takes a function, tears it up, throws it in the trash, and replaces it with another function. Method. With another method.
Functions, methods, whatever.
So typically you'll see the term virtual method or virtual function. It's used in both contexts. That's pretty much used in the method overriding context. A function, a method declared inside of a class that is declared as virtual is virtually replaceable.
So let's say, this is maybe not that practical of an example, but let's say you have a string that's considered to be an object, a number, and that number is an object, like an integer, but it's an object. That integer object might have a toString method on it.
Yeah.
So every time we print the number, we print it as a string when we call the toString. And that's built in. Well, we can override that method and write our own toString. So we can put like a little number symbol and then print the number. Or we can only print the number if it's less than 100 or something stupid like that.
Yeah. Well, once we get into actually programming an OOP, we're going to exploit this functionality.
Yeah. Maybe we'll just cut that out because that wasn't very useful.
Okay.
So this is very cool because we can overload the plus operator. So we can do this so that if we have our own objects, we have our own weird data types, we can change how we add them. So if we have a person object plus a person object, we can define how to actually use that.
Right.
Which is very cool. So let's take a look at an example. Let's say we have a number class and we have an operator plus. We have a number class instance 1 and a number class instance 2. They both have a private variable double number set to 1. So what happens if we say that this number class instance 1 plus number class instance 2 is equal to, naturally we would assume it to be 2, but we need to overload that operator in order for that to happen. So it becomes a very powerful way to interact with objects. It's just like if we want to say a cookie plus a cookie. Well, what are we actually adding between those two cookies?
Right, yeah.
Now, is it like the square, is it the total sum of the area of the cookies, or is it the amount of sugar in the cookies?
Right. Well, that's up to you as the programmer to decide.
Yep.
And that's what the operator overloading functionality defines. So abstraction, guys, the only thing really to get out of this is to go over the fundamental concepts that we discussed and understand that object-oriented programming is designed specifically to hide details from the developer that are not relevant to what they're trying to do.
Right, so when you write out your class definitions, you can write in there things like setters and getters to hide the direct access to the variables. Mm-hmm. We can overload operators so that we can say a person plus a person equals 700 pounds. Mm-hmm. We can, whatever we want, but we can establish rules so that we can work with the objects at a higher level.
Right. Mm-hmm. In this lesson, we're going to be talking about something that Brian does not have, and that's friends.
and something that neither of us have, which is inheritance.
Inheritance. So inheritance and friends. So these are kind of separate subjects, but they kind of have a similar function in object-oriented programming. Inheritance, Brian. Oh my goodness. Like, inheritance is one of the most important concepts to understand about OOP.
So we talked about abstraction. So inheritance kind of goes along with the ideas of abstraction with object-oriented programming. And what it basically is it inherits functionality from another object. Mm-hmm. So you're not going to reinvent the wheel every time you define a new type of object.
Right.
Why would you? Right. So if you've already defined a car, and it's only a leap to make an electric car, just inherit all the properties of a car,
right,
and make some modifications so that you now have an electric car, or a hybrid car, or whatever. So inheritance basically is just a convenient way of consuming all of the qualities of an object, and then modifying the rest and making it your own.
Yeah, so like when you have like a little kid blowing bubbles, and the bubbles fly together, and then they absorb into one bubble, that's really literally what you're doing with inheritance. And there's so many examples of inheritance throughout software development, especially when you get into like Mac, where everything is inherited from one object, you know, and C++ uses it quite a bit, C# uses it quite a bit. Like the disposable classes have to inherit from the disposable class instance. I mean, it's everywhere in object-oriented programming.
And friends is an interesting concept. Friends works the way human friends work in France and southeastern India.
Now, Brian having no friends, I can't wait to hear this.
So the way friends works in objects is you let friends touch parts of you that you wouldn't let anybody else touch. For those foo-foo fellas in France and southeastern India, it applies to you.
You know what's so great about that explanation? Is everybody knows exactly what a friend function is now. You let people do things to you that you wouldn't let anyone else do. I love it. I love it. Class inheritance. As we were just talking, it's when a class absorbs members of another object, and you can basically use these members as if they were native to you.
So let's take a look at an example of class inheritance. So let's say we have a horse object.
Yeah.
Well, the horse has some attributes like a tail and hooves, and it has methods like gallop, the action of doing something. So we have the horse, and now we want to create a giraffe. Well, we've already defined out some of the elements of an animal that we want to use in a giraffe, like the tail, the hoofs, and the ability to gallop. Mm-hmm. We just want to inherit those attributes and now extend it by saying it also has the attribute of a long neck and spots.
Yeah.
And it gives us a giraffe object.
Yeah, exactly.
Simple.
Another great way to think about this is, let's just say we make an object that's a person, and the person contains the fields name, birth date, and height. And then I want to write a software application that manages my employees. Well, if I already know what a person is, then all I have to do is have an employee object that inherits everything about a person, because a person is an employee, but an employee is not a person. And all that I want to do is add on their employee ID and their job code. So in this way, I've made an employee that inherited from the person class. So in a nutshell, just to kind of drill it in, here's my parent class with my two functions, which are really methods, in my attribute, and I have a child class. When my child class wants to pull from parent, now my child class has native methods and attributes that were once a part of the parent class.
Simple. So now let's talk about friend functions. And we'll try to do this as serious as we possibly can. In object-oriented programming, private members are not accessible from the outside.
Keep your fly up, Brian.
Yeah, exactly. As they should be not accessible from the outside.
I'm your friend, but I am not a friend function, okay?
Unless you're Pee Wee Herman.
Oh,
that's an old joke.
So friend function, Brian. In object-oriented programming, private members are not publicly accessible. There's certain things that you want to keep private. But let's just say you have a close enough friend that you don't mind sharing your privates with. So if I have a situation, Brian, where I want my privates to be exposed to you, I declare you as a friend function, right?
In some places, yes, that's true.
So the child class exposes a friendly function called myBuddy, and they have an attribute that is private that only their buddy can touch. So in the external code, we have a function called myBuddy that has exclusive access to the private member inside the child class.
So now let's take a look at class inheritance in the real world.
The real world, the world of David Bowie.
So, in the world and in the universe, we kind of have a natural class inheritance in nature.
Yep.
In nature, we have life, and then domain, and then a kingdom, and phylum, class, order, family, genus, species. And every time it gets with an increasing order of complexity.
Right. No, specificity. You were right.
Specificity, yeah. I didn't think of the word.
So when we think about class inheritance, we think of everything that defines life. So everything that is alive has all of these properties. And then we split that one point then splits out into many different things. So we have many different domains. So every single one of these domains in life has these different properties, but there is a ton of them.
And you wouldn't usually inherit a class just to remove all of its functionality. So usually when you inherit something, you don't become a simpler form of an object. Usually you become a more complex form of an object.
Right. You become the object plus plus.
Right.
So then in this case here, when we're looking at you sitting there watching this video tutorial, look at everything that you've inherited to get where you are right now. You've inherited life, and you're a complex-celled organism. You come from the animal class. You're a vertebrate. You are a mammal. You are a, what is that, a primate? You're a primate. You are a human man. You're a homo, and you're a sapien. So that, you inherited everything all the way up.
And each one of those inherited their parent.
And that's class inheritance in the real world.
Hope you enjoyed it. Welcome to our video on polymorphism. This one, don't get scared. It's a big crazy word.
I'm shaking in my boots.
But this is a very interesting concept. I think you're going to like this. Yep. Now, polymorphism is one of those topics where a lot of times in school they will sort of just breeze over because the teacher gets scared of the word and won't teach it to you.
Yep.
So this is where our easygoing content is just going to blow through and beyond what you're going to find in a college education, oddly enough.
Yeah, no, I'm
not saying that college education is bad. It's very good. It's good to have that structured. It's good to be able to have the certificate. But you're looking online to learn this stuff for a reason, and it's probably because you didn't really find enough information in the classroom structure.
Polymorphism is one of those topics that for some reason people want to make it out to be a bigger monster than it really is. And over the years, I've never understood this. And even people that have been coding 10 or 20 years, ask them, what is polymorphism? They will have absolutely no idea. They will have no way how to even approach answering that question.
I remember when I was in the last of the object-oriented programming classes, and the teacher said, "Oh, and if we have time at the end of the semester, we'll cover polymorphism."
Oh my God!
And I know like a half a dozen other people who have heard that same thing, and it never got covered in the class, which is weird because it's a very useful concept. So let's take a look to see what it's about.
Let's unveil
cool. I think you'll like this
scary monster that people don't want to know about. So polymorphism is basically when objects of different types can be compared as similar objects.
So let's say we have a cookie object and a cupcake object. So we want to compare these two things. We'll both have to have an interface that gets the amount of sugar, let's say. So in this case, we could say, is a cookie greater than a cupcake? And because a cookie has more sugar than a cupcake, it's true. So we're just setting a property on the different types of objects to expose sugar as an integer value or as like a float value that we can do comparison operations on. So similarly, we can say cookie plus cupcake equals 50 grams of sugar.
Yeah, that looks oddly similar, Brian, to that operator overloading stuff we talked about. Okay, so let's talk about like more of a textbook definition. So polymorphism is the ability of a programming language to allow multiple data types to appear and be used as another data type. So two examples of how this is used in programming languages are strongly typed languages, which are when data types all derive from one another, or loosely types, which is when data types are implicitly polymorphic. Now, so just to prove that we're not just saying this because we read it in textbook, a loosely typed language would be something like Perl, right? Where like you can have a string, you can have a number, you can have a boolean. It doesn't matter. Everything is the exact same thing.
Right.
You know, you could also have something that's strongly typed.
So, or like a strongly typed language like C, where every time that you use a variable, you have to explicitly define what that data type is.
Right. Yeah.
So, let's look at some common types of polymorphism. We have ad hoc, which is effective polymorphism just by like overloading operators and overloading functions to allow classes to conform to specific implementations. And that's just kind of conceptually polymorphism, but not actually declared so in a language.
Right. So it's not like natural polymorphism, but it's something that that you can make an unnatural language polymorphetic.
It gets the
job
done.
Is that a word? It is now.
It gets the job done. So we also have parametric polymorphism, which is code that's written with no data type specification, kind of like you were talking about in Perl, where you just sort of you have the objects and you kind of expose what you want to be comparable, and you just run with it. Everything's just
everything is the same thing no matter what it is.
Data types, and then you have inclusion. Inclusion is where objects are related by a common class or are typecasted as another class.
Right.
So you can compare them by typecasting them into similar objects, and that typecasting process will call methods that will convert the object properly.
Right. What are some characteristics of polymorphism? Well, basically, when you have a language where multiple data types respond to the same operators and method calls, you're dealing with polymorphism.
So that's seen often in superclass structures and class inheritance and things like that, because when you inherit a class, they're going to be very similar anyway. So you're going to have a lot of those similar method calls and property assignments.
Right. Like any of you guys that do any Objective-C programming, you know this very well. Because in Objective-C, data types derive from the NS object. Any object that uses NS object responds to the same method. So I want to get the value method. I want to get this method. Every single one of them has that method.
Right. The difference is that you overload the method for that particular object that you're working with. Mm-hmm. So an NS number has an overloaded method for the method that you're calling versus the just generic NS objects method.
Right.
So the purpose of polymorphism is so that developers don't need to know the data types when they're coding. I mean, it would be kind of a nuisance every time that you have this type of object and that type of object, you have to then write some other function to say like, oh, I want to compare these and access them and blah, blah, blah. We'll just bake that into the object so that we can just say this plus that or this object divided by that object.
Right.
Whatever the case. It's very cool. So it just keeps it elegant and keeps that level of elegance in your code so that you can just be broad stroking over what you want the program to do and not how to do it. So data types will be recognized and handled during runtime, which is dynamic binding. And different data types can share the same operators, which goes back to operator overloading.
Mm-hmm. Yeah, dynamic binding is a very important concept to understand, which we will explore more in depth when we get to C++. But that is kind of like the basis of understanding how polymorphism works during the runtime flow of a program. So we kind of seen polymorphism to a very small degree so far. Even though really, some people, I know that we're going to get comments about this, but structurally speaking, a float and an integer are not the same. Why? Well, because an integer stores no memory for remainders and for decimal places. It's a whole number. But I can still do mathematical operations on these uncompatible data types. So for example, if I take this C program here, I have float f 1.0, integer I 3, and character A. Okay, so we know a character is the same thing as an integer, but a float is not the same thing as an integer. So why is it that when I do C equals a float plus an int plus a character, why does that equal a number? Well, that's because these are able to be compared because of that small aspect of polymorphism that exists in the C programming language.
So how does this relate to object-oriented programming? Polymorphism, as we just saw, is not necessarily an object-oriented programming concept.
Right.
By definition, it is a characteristic of a language.
Right, like a language like TCL or Perl have it so baked in that you don't notice polymorphism.
Mm-hmm. But polymorphism is particularly valuable in object-oriented programming because every time you create an object, which is the nature of all of the programming in object-oriented programming, those objects are inevitably going to have to interact with each other. So it becomes a very widely used attribute of the object-oriented programming languages. So when classes derive from other classes, they share the same methods, but the methods may need to perform different tasks.
Yeah, so you guys may be wondering why we keep saying concepts over and over again. And that's because this is crucially important to understand. Now, when we mention that we have different methods that have to perform different tasks, take a look at this example right here, Brian. We have a shape, an object that's called shape. And every single shape has to be able to have an area calculated from it. So we just say, generically speaking, a shape has a getArea method. So now let's inherit from this object and let's create other shapes. So we have a rectangle, we have a circle, and we have a triangle. Each one of these inherit the getArea method. But the area of a rectangle is not the same as a circle. It's not the same as a triangle.
That's right.
So each one of these has to be handled differently. They are all going to be treated as a shape object because they all inherit from shape. So when I define the getArea method, I have to take into account that the areas will be calculated differently. But they will all be treated as a shape object. Doesn't matter what the shape is.
So now let's take a look at another example. Let's say we have a WibitFriend object. And that WibitFriend object has a method to make noise. So we then inherit the WibitFriend object and create a new type of object, a frog, a fly, and a chick. And they were all inherited from WibitFriend. Now each of those are going to have their own make noise function. But the make noise function is going to produce a different result for each of those object types. For example, the frog, the fly, and the chick will make noise like wibbit, bzz, and cluck.
Cluck! Cluck you! I don't have to even beep that one out. Cluck you!
So how does this relate to object-oriented programming? Well, let's say you want to add a frog and a fly.
Yeah.
What do you get, Kevin?
You get a frog fly!
I don't even know what noise that makes. It's
Bezorbit.
Alright, now let's talk templates. So templates are available in some object-oriented programming languages. And what this does is allow data types to be seen as any data type.
Right.
So it allows you to, let's say, define an array of some object type, but that object type is just any object type.
Right.
So you kind of have a template form of whatever that object's going to be.
You could even take that a step further, and you could have an array where each element can be any data type.
Right.
So not just like one, like, not that you can define it as any data type, but I can say this element is this data type, this element is this data type.
Right. So in the array, you can have 2 frogs, a fly, and a chick.
Right. Yeah. They don't have to be of the same type.
Right.
Yeah.
Very cool. So code is designed with no data type specification, and we write code around that. So it has the assumption built into this template concept that all of the objects that we'll be working with will be properly polymorphic, because that's how we can write code generically to handle the interaction of objects.
So templates can be either used on a function outside of a class or a method inside of a class. So let's just say, for example, this is a function that exists inside of a program. So we'll just say function generically. And it adds 2 numbers. And as you can see, we have these little gray circles here. Now the gray circles indicate that there is no data type specified. The only thing that we know has to happen is there has to be a plus overload. So whatever comes in, I add the 2 together, and whatever the plus overload does, I return that back. So now I'm going to send in the red ball. So when the red ball comes in, the red ball is what's going to be returned, and the red ball is what's going to be compared. So then I send out a red ball. Now I want to call this function again, but I have a different data type, a green ball. So the green ball comes in, now the green ball return type goes out. So no matter what the input data type is, this function doesn't care, because it's templated. Whatever comes in, it does its thing, and it sends it out.
Very cool. So templates depend on other object-oriented programming techniques. Like we were talking about, it depends on inheritance, it depends on operator and method overloading, and these are things that allows for polymorphism.
Right.
So this is not dependent on primitive data types.
So how scary was that, Brian?
Not bad at all.
Polymorphism, we just explained it as if it was a Saturday morning cartoon, and for some reason, professionals have no idea what this is.
I think they just take it too seriously.
Yeah.
I hope you enjoyed it.
Yeah. Ladies and gentlemen, welcome to the video and the introduction to OOP on delegates. Now, this is another great concept that is used an awful lot in software development, and it's talked about an awful little in software development training for some reason.
I think because it's a freaky concept.
It's no more David Bowie?
No, I'm trying not to. I'm trying my best.
David Bowie is going to try to get royalties from this website.
So delegates are very cool. Let's just jump right in. I think you're going to like this.
So delegate is really an agent, right? It's something that acts on behalf of something. So it's basically running code that exists in one class inside of another class. So in a very basic sense, you're sending a function as a parameter to a class. Yeah.
That's exactly it. It's instead of passing a variable as a parameter, you're passing a function.
Yeah.
So for those of you who are looking at learning this object-oriented programming for the sake of learning something like Objective-C, the delegate concept is absolutely necessary to have nailed in order to start programming in Objective-C.
Right. And to a lesser degree, C#, because Visual Studio actually hides that concept from you, but it's still there. It's used for everything. It's just that they don't let you see it. Abstraction.
Right. But if you start doing like iPhone, iPad kind of stuff, whatever programming.
Of course, it's 2025 now, so let's see what will be popular. iShoe, yeah.
No, the I.
The I.
You swap out your eye and you get a visual cortex.
Apple's on their way there. So why would I want to use a delegate? Well, basically, any circumstance where a customization is necessary within a structured piece of code. Now, take that definition for what it is, because we're going to kind of go through this, and that will define itself as we go through.
Yeah. So why are we doing this? Well, this allows us to expand the functionality of class any way we want.
Yes.
So classic examples of this are going to be the GUI events, like when you click a mouse and click a button, and that calls anything in like the model view controller kind of structure, the TCP listener stuff, or even a remote controlled car. What the hell?
Look at this little boy. All right, Brian, help me figure out how this happens.
Does this boy have a friend function?
Michael Jackson? I don't know. He's dead now.
So let's walk through just a very basic, like we're not saying this in a condescending way. We're just saying this in a sense of Like, we want to just make some sort of relevant story arc to define out what a delegate is.
And I am saying this in a condescending way. I'm smarter than you, and I want you to feel stupid.
So the delegate concept is something that is easily miscommunicated because it's such an abstract concept.
Yeah.
So we're just going to start with an extremely basic concept, and you know, sometimes even we'll do things where we think we understand something, and then we'll see it in a simple form, and we're like, oh, that makes a lot more sense.
Yeah.
So I hope you like this. Bear with us.
So this is kind of like the recursion cartoon that you did before.
Right.
It's following that same example.
So let's say we have a kid. He has a remote control, and there's a remote control car.
Yeah.
The car is waiting for a command. So the car has been designed and built with a lot of actions that will be triggered by commands, and it's just waiting for the command. Without being controlled, it'll just sit there and wait. It won't run. It won't do anything. It's just sitting there, waiting for a command.
So here we have a person object instance and a car object instance. Now the car exposes its functionality to the person via the remote controller. So it has a lot of functionality, but the functionality can't be manipulated unless there is a device controlling it. So in this case, the remote controller will access the exposed functionality of the remote controlled car.
So the remote controller in this case is the delegate function called in the person instance to control the actions within the car. So the person object has kind of consumed the controller from the car because the controller in the car kind of came in a package.
Right.
And that person object consumed that controller, and that controller is kind of wirelessly linked to the potential actions in the car. And when that person calls functionality in that remote controller, the car will perform an action. So the person creates an event that performs a delegated action in the car. Pretty cool, huh? So we have two objects that are interacting with each other by way of an intermediate function that's kind of inherited from the car.
Without absorbing each other and becoming one.
Right, so it's not like the person has the car function or the cars become part of the person or anything.
Right.
So what do we want to take from this example? Well, a couple things. One is that a car is performing a default task without the remote controller, and that is to do nothing.
Yep.
So the person can't control the car without using the remote controller. So the person had to have consumed that remote controller, right, or that delegate function.
Because we can't control with our mind. The kid, well, not yet, not until the Apple II comes out. You can't control it with your mind. But the remote controller allows the person to control it through an intermediary.
So the remote controller exposes the car's functionality to any entity that can use it.
Right, so if it doesn't have to be a person.
It could be a monkey.
If you have your remote control and you lay it on the floor to get something to drink and your cat steps on it, the car will still react to that cat. So it's not object specific.
Right, so that remote control is still acting as a delegate for the cat to control the car. So the remote control is a predefined method of using the car.
Right.
So the person didn't create it.
No, a person may have created it, but that specific person that's using it did not create it.
Right. And that remote control that was created for the sole purpose of controlling that car.
So it's not like he happened to find the remote control that happened to work. It was made on purpose.
For that particular object.
Right. So if we start talking about, GUI buttons, right? Like, how much would it suck if every OK button on every program did the exact same thing? How much would that suck?
That would be pointless.
So if we take a look at this little GUI button, this little dialog window here, each button is an instance of the same class, and it's an instance of a button class. So right here, I've created my own object, and it's called the remote code object. So I've created an instance that has a function that says do action. So this is a function within my class that I would like to implant in another class. So over here I have my little OK dialog box. So when I click on the button, I have a default action, which is to do nothing. And if you take a look at our little graphic here, there's a little star thing that is waiting for someone to attach to it. So please attach to me because I don't do anything without you. So I say, okay, I'm going to fly my little connection here and say, I'm going to send you my location. So here's where my object in memory is located. Now, the onClick method recognizes that, connects to where the function is located. So now every time that I click the OK button, the signal goes to my onClick method, which goes to my delegate. So the important thing to get from here is the code that's being executed, although is triggered by the button object, is executed inside the remote code object.
Right, so this onClick method has a delegate pointer.
Right.
To a reference location in remote code somewhere else. So it's not calling the code inside of the button. It's just calling a command that sends itself out to wherever it's pointing to. So the OK button and the cancel button can be of the same object type.
Right.
But the onClick events can have delegate pointers that point to different memory references. So the cancel button still has an onClick and it still functions the same. It still has a title and the name and the display and the size and the width and everything. But when you hit on click, that goes to a delegate pointer that goes to the cancel functionality, whereas the OK button delegate pointer goes to the OK button functionality.
So a very classic example, at least I think a classic example of delegates is a TCP listener. So when you write a TCP listening class, you should have a default method of managing responses to the client. It's I send you a message, you send me a message back. So maybe my server accepts a TCP transaction and responds with, got it, thank you. So the programmer that writes the TCP class should not be responsible for knowing every single way of responding to a client. I mean, it's not even possible. There's not even enough lines of code in the world to do that. So what you want to do as a programmer is write a TCP listener that has a default method, but also allows a programmer to use that as a delegate. So when a transaction comes in, it goes off somewhere else for processing. So you're sending out to someone else, your delegate, your agent. Your agent then responds back to you, and then you handle it as you would normally do in your response process.
Cool. So let's take a look. Let's walk through this example. So somewhere out in the internet, somewhere out in the cloud, in some unknown, unspecified CD location.
It's the World Wide Web.
So we have a TCP client. Now we have built a TCP server that has a listener method and a process transaction method. And then we also have, separately from this, just my class that has a method in it to process a message that performs an action on like the meat and potatoes of processing a message, which kind of consumes some resources.
On this specific type of message, right, so to speak.
So my class sends the location of process message over to the TCP server's process transaction delegate pointer. So process transaction now has the location of the method in my class process message.
Wow.
Very cool.
There's your delegate. There's your agent. Yep. You sent your agent, and now he's occupying the foreign country.
Yep, exactly. So now when a TCP client sends some sort of packet to the listener receives that packet and sends it on to process transaction. Well, that's not going to be processed on the TCP server. That's actually going to be processed remotely by way of the delegate function in my class, in the remote code.
Exactly.
Very cool. So that will do its thing.
Look at this.
While TCP server is still doing its thing.
But look, the message is now completely encapsulated in my class. It's not even in the class that it originated from.
It's totally disconnected.
And then it goes to the Ninja Star.
And then it'll send the result back to process transaction, which handles the return of this to the listener and sends back to the TCP client.
How cool is that?
I know, it's
That's
awesome.
Amazing.
So that is delegate function. So I hope that helped to really drill this concept in. The delegate function is really just an agent on behalf of some other remote object.
Right.
Simple.
You have been delegated!
I don't even know what that means.
I don't even care what it means. It sounds awesome. So, Brian, you may have some simple questions.
Right.
Like, is a delegate also an API?
Not fundamentally, but functionally, pretty much, yeah.
But not. Because it's not really an API.
But functionally,
it has the same kind of essence as an API. So, Brian, are delegates used frequently in software engineering?
Of course. Absolutely. They're used everywhere, all the time. They're inescapable.
Well, then I got another question to ask you. So, like, how are delegates different from inheritance, method overriding, and method calling? So why couldn't I just have the TCP class, call a predefined function somewhere else?
Well, let's take a look at our example originally. In the case of the boy remote controlling the car, the boy doesn't become the car.
Oh.
So no inheritance can take place.
Right.
So the two instances interact without becoming the same object. So they still remain separate, they still remain remote code, and those different objects can execute and utilize resources in different locations, but still interact with each other. This is essentially method calling, except the accepting class is going to run my code, not theirs.
There you
so
go.
I'm not saying, hey, you go run this code, I'm going to create an instance of you and run you. I'm just saying, hey, we're connected, and I'm calling some of your functionality remotely.
So here are some other non-programming examples of delegates. So here's a good example. When you are using a computer and you use a mouse to click a button, you are using an intermediary to act on your behalf. So the mouse inserts your intents onto the computer for you. You don't actually connect your brain. I wish I could. Goodness. Connect your brain to the computer and even then you're not really directly doing it.
Right.
But you're using that to manipulate the machine.
Right, or changing the channel on your TV using a remote. The remote controller sends a signal to the TV on your behalf.
Right.
Similar to the remote control car example.
Right. So here's a bad example. Driving a car is not a delegated action because you actually actively insert yourself into the car and drive it.
Right.
So that's not a delegated action. That's a direct action.
Right. That's a car consuming a person for functionality, right?
Yes. Also, changing the channel on your remote, changing the channel on your TV by actually getting up and pushing the button on the tuner.
Right.
That nothing's working on your behalf.
Right.
Do you have any other good ones to add?
No. So these are some examples to kind of drill the idea further into your mind. So, we think with delegates in particular, examples are, just thinking of the concept of delegates is really where you're going to absorb this concept. So I hope you enjoyed it. I hope you now understand what delegates are. So if somebody comes up to you and you're like, I'm trying to write this thing, but I'm stuck on this like weird delegate crap. It's all going backwards in my brain. I don't understand what's happening. Can you explain it to me? You can be like, oh yeah, it's easy. It's like, the delegate function is like the remote controller for somebody controlling a remote control car. Like, easy. Done. Not a problem.
Done deal.
Yeah.
In this video, we're going to talk about open recursion and namespaces. Now, open recursion and namespaces kind of sounds a little bit foreign. We're going to make these concepts airtight in your brain right now. So what is open recursion? It's basically the ability of a programming language to access members within an object instance. So typically keywords are used to access variable names. In a lot of languages, you'll see things like this, self, or me.
So this is very similar to recursion like we talked about before, where a function can call itself.
Mm-hmm.
So the function isn't really like a concept of an object. It's just some accessible function that we can call, and inside that function we call it again. It's kind of the same thing with an object, but when an object instance has a method that calls that instance's method, then we get recursion inside of the object.
Right. So these keywords will typically represent a pointer to the space of memory where that specific instance of the object is located.
Right.
In a lot of programming languages, either force you to use it or assume that you use it. So it can be kind of tricky. PHP is one way, Perl's one way, Objective-C is another way, C# is another way. You just kind of get used to that after a little while. And me is stupid. That's what VB uses. Come on, open me?
So how does this relate to object-oriented programming? So a lot of these languages suggest this usage as you were just describing. And these keywords are really just essentially, just to reiterate, they're just pointers to the current instance. So it's really just when you write the code in your class definition and you want that object to refer to itself, you just say, self dot property of object, and there you go.
So here's an example of accessing a method inside of a class using external code. Now don't pay any attention to the syntax. This is arbitrary syntax. It means absolutely nothing. So let's just say our programming language, which is Brian++, allows you to create a frog by evoking the frog object, creating an instance called myFrog, and making a pointer to myFrog by calling a new frog. So let's say I want to access the makeNoise method. Well, in Brian++, we do myFrog.makeNoise function. Simple. So let's say inside of myFrog, when the external code accesses the makeNoise function, it wants to call another function that is within that specific instance of a frog. How does this work? Well, if this were to be the code of the makeNoise function, so we're returning a data type called noise, and what we want to do is call the getNoise2make function. So when I use the keyword this, it's referring to myself. And then when I do this dot in the name of the function, I'm saying within myself, call this function.
So it's pretty straightforward. Now let's take a look at namespace. So namespace is a logical...
Bowie's in space.
Bowie's in namespace. What you doing out there, man? The namespace is a logical grouping or container of classes. So it's a way to kind of refer to we kind of talked about before, we can make our own little ecosystems of classes and stuff.
Yeah.
So a namespace is really kind of defining a little ecosystem of classes.
Mm-hmm.
So it's just a logical grouping of classes to keep organization. Some languages also will allow the usage of fields and functions too. It just adds an extra layer to the object-oriented model and just kind of helps for categorization, organization, and keeping your clean code.
So let's just say we have a little series of bubbles here, right? We have our main bubble on the upper right, and then a bunch of supporting bubbles that have their own specific functionality. So in the main bubble, that's my program namespace. Now over here on the left, I have a console namespace that has classes that have to do with working with the console. And then I also have a file namespace that has classes that have to do with working with the file system. So they're neatly categorized using namespaces.
Convenient. So instead of having one major nasty list of functionality, we can say console dot
something dot something.
Yeah, something weird like WriteLine. I don't
know. Something weird.
So classes in different namespaces can access entities by one of these ways. One is by using the namespace, and by saying we're going to use this namespace, from that point forward, we don't have to call the namespace anymore. It's just assumed.
Right.
Or we can directly reference the namespace. So every time we want to call something inside of a namespace, we say the namespace name and then what's inside of it and so forth. So namespaces can contain their own namespaces to further categorize entities. So you can really, layer this out if you want to.
So in a circumstance where you have two different namespaces that have a class of the same name, you don't want to use those two namespaces because there'll be a conflict.
Right.
So in those circumstances, you would want to reference the namespace. So there are different circumstances where these are best used. So let's just look at an abstract example, Brian. Let's take a look at Bowie in space.
In the universe.
The universe. So here is my namespace called the universe. And inside my universe namespace, I have a class called the Milky Way.
That is one ugly Milky Way.
That is I wonder what kind of a sick man would have made something that horrible. So inside of this Milky Way, which has a supermassive black hole in the center, by the way, we have another namespace. This namespace is the solar system. So inside the solar system, we have classes and methods that deal with solar system things like the planet Earth.
And then inside that, life and other things and species, and then you.
It's all starting to come together.
So let's take a look at a practical use of namespaces. So let's say we have a large namespace called system.
Or the universe.
And we have other namespaces like collections and IO and console.
Or Milky Way.
And inside IO, we have something like file.
Or solar system.
Exactly.
I'm sorry.
Yeah. So we want to call something in the console to write out text to the console.
Mm-hmm.
So we would call system.console.write, which is one of the methods in console. So we call the system namespace, and then we refer to the console class, the static class, and then one of the methods inside called write, and we pass it the parameter text. Now we can also do the same thing with like system.io.file append text, and in this way we can keep going namespace, now down to static class, and then method to be able to access the contents of a namespace. So this is really just a very nice, clean way of, instead of just saying append text or write, it's like, what are we writing? Are we writing text or are we writing something to the console? Well, this way we can say system.console.write and it'll write to the screen, or we can say system.io.file.write and it'll write to a file.
Mm-hmm.
It's very nice. So it's pretty straightforward. So that's namespaces and
open recursion
and the universe,
the galaxy,
yes,
and Bowie in space.
Yes. So it's a very useful technique for keeping your stuff organized if the language supports it. Welcome to our object-oriented programming video on properties. Properties is something that we alluded at before when we talked about setting and getting, and we talked about there's private attributes that we might not want other things to have direct access to. So we can write methods that will get and set that value in a way that we can have control over. Well, properties is that in an official sense.
Yeah.
So a property is kind of like a variable, but a property must have a setter and a getter to access that variable. So let's take a little look at them. Just a warning, this concept of a property is not supported in all object-oriented languages.
Yep. Now you'll also wonder why earlier we said that people will refer to fields as properties and why that's incorrect. When we get to the end of this video, you will understand why that's incorrect, because it may sound intuitive to call a, like Brian's first name, a property of Brian. You'll see that technically that is not the case at the end of this video.
So what exactly is a property?
Well, I don't know. What is a property, Brian?
I don't know. A property is effectively a mechanism that allows the reading and writing and computing of private field. Because a property really doesn't actually have to tie to a particular attribute. A property could be something that calculates. So if you have like a time property, you don't actually have to have a time variable that it's referring to. When you get that property, you could just get the current time.
Right.
And when you set that property, you can then just, set your system clock or something.
Right, yeah. Something a lot more abstract than just setting a variable. But it acts like it is a variable.
Yes,
it acts as, that's the whole abstraction thing.
Right, so you use it just like you'd use a variable. You don't actually call the set and get methods, which is very cool.
Yeah.
So there's only two allowable actions. Like we said, there's just a set and a get.
Mm-hmm.
Properties are considered to be members of a class just like a method or a field.
Yep.
And you interact with it just like you would a field.
Exactly.
Object-oriented programming is that languages that use properties implement them differently.
Mm-hmm.
You know, but
they're typically used the same, but the way that they're created are usually different.
Right.
So why use a property, Brian? I mean, we've gone over this before. You know, let's say we want to make something read-only, where we want private fields not to be completely exposed, so we will let you read it, but you can't change it.
So in other words, you could let a friend look but not touch.
Well, no. If it's a friend, they have full access.
Yeah, that's right.
So what if you want to also just indirectly set and get? Now, this just may sound like a stupid, idiotic thing to some people, but trust me, there are so many ways that this is practical, like in the example Brian gave, where you're setting the system clock. You're setting a variable. The act of setting that variable fires off setting the system clock. So it is a very practical use. It also provides a simple way to return calculated values, and it acts just like a field. So if we wanted to get Brian.yearsold, it will take his birth date, subtract it from today, calculate how many years that is, and return the value.
And if we set how many years old I am in the same thing, we can reverse engineer how old I must be,
right?
Or when my birth date was based on how old I must be, we'd set it.
Right.
And set the birth date of, that date value.
And you also want that birth date value to be private and not changeable, only read only. Because if I can just make you 5 years old right now, how funny would that be? Right. Just make it little 5-year-old. Would you still have the beard?
Probably,
maybe?
Yeah. So let's look at a basic example. So let's say we have a car, and the car has public and private members. The public is some methods like miles per gallon, miles driven, used gallons of gas. And the private attributes are variables such as driven miles and burned gallons of gas.
Right, because you can't change how many miles you've driven. That's why this must be a private, unaccessible method, or field.
So when a remote class calls the public property used gallons of gas, it will get the private value and return it. Similarly, if it calls miles driven, it's going to access the driven miles variable and return it. And lastly, if we call the miles per gallon, it will perform a calculation of the driven miles divided by the burned gallons of gas and return that result.
Simple, right?
Yeah.
So how is this different than methods? Well, functionally, it's not. Like if you wanted to have a setter and getter method, this actually works the same way, functionally speaking, although technically it's not. The usability and the ease of using these properties over methods in many instances are a lot easier, a lot more beneficial.
But the way they're defined is similar. So you do have a block of code that you write out what you want to do and you return a result back.
Yep. So that's basically it. There's really not much more we can say about properties.
Yeah, so you will find yourself with circumstances where you'll instantly appreciate the value of properties now that you understand what it is. Play around with it, make some objects in your language of choice, make some variables and make some properties, and make the variables private, and just kind of get a sense of how that implementation works in the language that you're using.
Or later on, when we take you guys on your journey to being the greatest software developer ever, and we start talking about properties in OOP languages, we don't have to explain it, because now you know what a property is.
You'll just be using it with us. We'll just show you how to implement it.
Hey everybody, welcome to the Introduction to OOP tutorial series. In this video, we're going to talk about two amazing aspects of object-oriented programming, the constructor and the destructor.
Right. Anytime you have an object, that object either has to be created, and once it's created, it must be destroyed.
Exactly.
Because, well, this isn't necessary, right? But like E = mc squared, energy can't be created or destroyed, but objects can.
That's true. Well, technically not, because the memory's still there.
Right, so all said and done, the memory ends up zeroing out to nothing. Yeah. Just like energy in existence. Right. So if you want to have an object exist, and if you want an object not to exist, you have to know how to construct it and destruct it.
Exactly.
So let's take a look at how this works.
So a constructor is sometimes initialization is a hard word to get out.
It's like statistic.
A constructor is an initialization method that executes when an instance of an object is created.
Right.
Isn't bad. I got through that pretty good.
So when a person becomes some particular person, that instantiation process is happening by way of a constructor.
Right. So initializing an instance prepares the instance for use.
Right.
So it can either accept nothing. It could also accept, startup parameters, that kind of thing, which we'll get into here in just a few moments.
So what kind of things can constructors do? Well, constructors can initialize instance level members like attributes or fields. So we want to say here's an example. When a new block of cheese is created, the expiration date is assigned automatically, and the type is defined by the calling code. So when we create a new block of cheese, we also initialize it with an expiration date. It also can return a pointer to the memory where the new instance is located. So the pointer, a variable, a label, and the calling code knows where the instance is, and that happens from the constructor.
Yeah, because many OOP languages, whether they show it to you or not, sometimes they hide this in the code. They do treat objects as pointers exclusively. But a lot of times they just hide that aspect of it. So the constructor, no matter which constructor is called in a program, at the end of it returns back where the pointer to that location of memory is.
It can also be used to initialize class level or static members. So, like for example, our class level definition has something like population, but our instance has, the person's age or something. Well, when we call that constructor, it can also initialize class level members and do things like increment that class level population attribute by 1.
Right, so that I can ask, hey, person, how many people are there? And the person responds with whatever that number is.
Right. So it's extremely valuable.
So let's take a look at a basic constructor. So here we have our frog, and we have a static field called population, which is set to 0. So every time that we create a frog, we execute the constructor, and this constructor increments the population by 1. So now we know that there's 1 frog.
Right. So as you'll notice, the constructor method name is the same as the class name.
Right.
So if the class name that we've defined is called frog with an uppercase F, the constructor method will also be frog with an uppercase F, parenthesis, and then we can pass in parameters if we want or whatever we want. We can overload the constructor. We can do all sorts of, just like we normally would with a method. But that method name will be the same name as the class that it belongs to. And so we want to make another frog. We call the class frog and we call the constructor frog, and it returns us back a new frog and increments that global level population attribute, the static population, to 2.
Call it again. Now we have 3 frogs. So in this example, we didn't instantiate instance level properties or values or fields. The property or field that we were working with is a static level field, which means the population belongs to the frog class, not the instance of the frog instances.
So let's take a look at the destructor. A destructor is essentially a method that executes when the instance is being destroyed.
We're killing it.
And eventually we're going to run out of memory if we keep creating instances of stuff, so we'll inevitably want to destroy objects when we're done using them.
Yep. So what are some things that destructors do? Well, it deallocates other members within the instance to clean up memory. So if you were to create an instance of a person, and inside of that we had an object called a string, and inside that object we stored the value Brian. Well, at the end of this object person's existence, if we don't destroy the string object of Brian that exists inside of the class, we will create a memory leak condition. So destructors are very commonly used to free up memory that was dynamically created during the object's instance existence.
Otherwise, we run a program for 10 minutes and it keeps consuming more and more memory and we don't know why, and then the computer crashes.
Yep.
The destructor is also used to update or manipulate static fields, just like the constructor did. So a destructor can also update or manipulate static fields just like the constructor did. So, for example, just like the constructor would increase the population of the person class, the destructor can decrement that value when we destroy it.
Mm-hmm. So each time a person instance is destroyed, the population dies. Now let's take a look at that using the frog example. Here we're going to deallocate the frog. So we're going to say destruct. Now we're going to, Brian, struck by lightning, gone. Now you see, look at the population's decreasing. So let's kill the last frog. Bam! Population is now back to 0. And that was all handled by the destructor inside of the instance of each frog.
Nice. So in this case we have a person concept. We have a person class. Some definition of what a person is. And a person has attributes. They have a name, a date of birth, which implies an age, and a gender. We also have methods of a person, like speak and reproduce. And some of these have considerations in the methods, like, for example, to reproduce, the person must be female. There's also attributes of people as a whole, like population, for example.
Which we've discussed already. So here's our little person bubble. So the attributes of a person that we have defined will be set out like this. So if we go to this next slide, you'll see that our first name is a char star and our last name is a char star. Are we starting to marry these to programming concepts? I wonder what's happening. So now let's go to the birth date. Well, the date of birth is going to store a long integer? Could that possibly be Unix time? I don't know. Next, we're going to store the gender, and the gender is going to be a single character, and that will just be some sort of a gender code. Now, each one of these, in this magnificently complicated maze of arrows, is either accessed or set by other methods. Now, we're not using properties in this example, we're using setters and getters. So, for example, the setFirstName method will set first name, the getFirstName method will get first name, and so forth. You'll also notice that the constructor is the only thing that will set the date of birth.
So now let's make methods to set and get, not necessarily properties, but in this case we'll just use methods, to set and get sort of an interface to all of the private variables that we don't have access to. So if you look at the bottom, in the public domain, we have the constructor, which will set the date of birth and the gender. And we have our destructor. And we also have things like setFirstName, which will set the, first name variable, and getFirstName, which will get it, and so forth. And things like getGender, which there's no set gender, there's only a getGender. Or a getBirthDate, it just gets the birth date. But the constructor will set those. So we now kind of have control of how these things will be interacted with.
Right, because when you're born, you don't pick your gender.
Right.
You don't pick your birth date.
For the most part.
You could surgically change your gender, but that doesn't change the gender you were born with. True. You know? So that's a property of you that's decided at the second that the instance of you is created.
So now let's take a look at something that's not a setter and getter that's directly wired to one of the private variables. So this is like the getAge, for example. So getAge will go out, it'll look at the date of birth value, and it'll take the Unix time now minus the Unix time of the date of birth, and it will return that result back to getAge. Very cool.
Yeah. So now let's take a look at these other methods. We want to be able to speak and reproduce. So this person is pretty boring. When we want to speak, we call the speak method, and we pass the speak method what we want to say. That's one of the parameters. So what I want to say will come across. Then if I want to reproduce, I can create a new person. Now inside of this reproduce method, it has to check, are you able to reproduce? Are you a female? Because a male can't reproduce, only a female can. And if you look at the return type of this method, it returns a new instance of a person.
And we also have the static long population, which is the attribute of people as a whole.
Yeah.
And this is accessed by way of the constructor and the destruct. So when the constructor is fired, we increase by 1, and when we destroy the object, it's decremented by 1. Now this is accessible by the static method getPopulation. So that's not called on the instance of an object, that's called on the person class.
Yep, and it only allows you to read the value, not manipulate the value. So let's take a look at this Brian++ code example here on the right. So here we go, Brian. Let's create a new instance of Brian, my person, Brian, or Wibbit, whatever. So what this is going to do is this is going to fire the constructor. Fire! When the constructor fires, I set the birth, I set the gender, I increase the population by 1. Brian, now what happens?
Now we want to set the first name. So we set the first name to Wibbit. We set the last name to .net. And if you notice, we're calling the myPerson.setLastName method.
Right.
So we pass in .net. Now we print out what's the gender. So we'll say getGender, and then we'll also print out getAge.
Which performs a calculation.
Right. So getAge isn't just dumping out some value. getAge is actually making that calculation happen on date of birth.
Now we want to call a static method, Brian, but we don't say myPerson.
Right.
We say person.
Right. So now we're calling the class .getPopulation, not the instance. Because the instance doesn't have getPopulation.
Yeah, only the class level. That's why they call them class level access.
It's nice. So now let's create another person, and that new person will be stored as the result of myPerson's method call reproduce. So we won't talk about try, catch, and exception handling. We'll just assume that, that Wibbit.net is a female. And we'll delete myPerson, which we'll call the destructor, decrement the population. And then we'll call the new person, print out the new population, which will take us back down to 0.
Yeah, so what we've done is we created 2 people, we killed 2 people, and we showed some attributes of those 2 people and the person class as a whole.
All in a day's work for Charles Manson.
How can we wrap David Bowie into this? That's good enough for me.
Hello, everybody. Welcome to a very interesting topic on reflection.
Yes.
Reflection's not necessarily something that we were going to put in Intro to Object-Oriented Programming, but I think it's worth a mention at least.
Yeah,
at the very least, one day when you're in a job interview and someone asks you this just because they think that they're cool, you'll know what they're talking about. And you know how to fire back, and then you'll piss them off because they're not as cool as they thought they were.
And maybe there's a freak case you might use it. It's possible. We'll see.
Yeah, we'll see.
What is this? You might have heard about it.
All right, so Brian, what is reflection?
It creates a circumstance where a program is kind of aware of its environment. I guess you could say. The program can kind of monitor itself and its program flow and dictate the next course of action based on what it has access to. That sounds kind of confusing, so let's see if we can kind of clear this up. When a program executes in object-oriented programming, it creates objects. And there's an entry point in one of these objects, which would be the main object, and then you kind of go from there from object to object to object. All of these object instances are all kept track of by the runtime environment, so we know what's been instantiated and what we can instantiate and what classes we have access to.
And the templates for what you are able to create are there. So in C++, for example, when you get to C++, there's a string object, right? So the program is aware that there is this object of a string.
So we know if we were able to create a person and we created a person Bill, the runtime environment knows that not only can we create a person and that we have everything we need to make them, but we know that Bill's been created already.
Right, and we also know what people are.
Yep.
So not only are you aware of that specific person, but you're aware of people in general.
Yep.
Just because you've been exposed to that in your environment. So when you and your mate want to create another person, you are aware of making another person. You know how to make another person. So you do. So in computer terms, right, in a very classical way of looking at how computers process data is the instruction data model, where if you look at this diagram on the left, we have a list of instructions, and on the right-hand side, data that the instructions will manipulate. So in a classical sense, in procedural programming or procedural languages, like C, for example, is a good example of one, we can have an instruction. And the instruction is a simple assignment where I want to set y equal to x 10 plus 1. Well, those values are stored in memory somewhere. This is the data that's being processed. Notice, Brian, that there's a separation between these two in the classical model, right? Mm-hmm. So the instructions are separate from the data that they're working on. So in this particular case, I'm going to, basically send these two values through some sort of an adder and then store the result in another a data cell, and now I can have access to the results of the instruction that I just counted out.
So that's the classic way, that things work. In reflection, it's a little different. You can kind of think of reflective programming as is more true to everyday life. You yourself are an instance of a person object.
Right, yeah.
Everything around you is also an instance of a car object or
underpants,
an asshole object, whatever,
bar of soap object.
And so everything that's around you, all those instances are observable to you. Right. So I have a fork and a knife and I can cut my food. I don't have a fork, but I do have a knife, so I have to hold it with my hand. Mm-hmm. You understand that. You're kind of self-aware in your environment and of your environment.
Right, and as you're walking across the floor to go shower up in the morning and there's a big gigantic basket of dirty clothes, the reason you don't run into that is because you are aware that object exists. And if you have a pet cat that you're about to step on, the cat runs away because it's aware of you.
Right.
So it kind of works in multiple directions here.
So are you still confused?
I'm very confused, Brian. Maybe a picture of the frog can help us out here.
Well, he just looks as confused as we do.
He certainly does.
Oh. Okay.
Okay, so in this diagram here, or in this picture, we have Wibbit the frog, Buzzy the fly, and Chicky the chick. I don't even know what the hell their all names are. But Wibbit the frog, who's going to be the focus of this, is aware that there are two other object instances in his environment. So let's just say, Brian, for example, Wibbit the frog wants to talk to the chick. And he has the power, he has the power to think this, first of all, but now he also has the power to go out into the environment and ask. He goes to the fly and says, "Are you a chick?" Now this is kind of interesting to examine here, because what the frog is doing is he's going out to a random instance. From his perspective, he has no idea what this is.
Right.
But he is just asking the instance, "Are you what I'm looking for?" And the instance says, or he says no. And then he goes out to the chick, and this is what he wants to communicate with, so they can have their two-way conversation.
Right. And that's effectively reflection. So reflection is kind of do I have a class that I can create an instance of? Do I have this instance?
Right.
Oh, I do. Awesome. Then I'll use it.
Right.
And if I don't, then I'll just do something else.
And in this particular case is, do I have this specific type of instance available to
Right.
me? Right. So, Brian, what just happened?
So the frog was aware of the fact that there's at least objects of some kind around him. He's aware of the surrounding instances, not necessarily immediately what they all are. And he knew he wanted to interface with a certain type of object, in this case the chick. So he went out and iterated through all of the possible objects and checked to see if which one was a chick, found the chick one, he found it, and then he interacted and sent the instruction.
And that changed the process flow of the program, because had he not found the chick, then the process would have gone to a different way,
Right.
a different
A
method.
mitigative action.
Exactly. So here's another one, Brian. What do we got here?
So in this case, we have the chick
Yeah.
that needs a blue frog that likes French fries.
Wow, she's a very picky chick.
Right. She's demanding.
Yeah.
I want like a blue frog that likes French fries. Are you a blue frog? Are you a blue frog? Are you a blue frog? Are you a blue frog?
Okay.
Oh, you're a blue frog. What's up? What's up, honey? Do you like French fries? No. Well, then screw you.
Wow.
Are you a blue frog? 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 You like French fries? Yeah. Woohoo! Awesome. Let's get married.
Wow. I wish real life was like that.
That's Match.com in a nutshell. Match.com is reflective programming for humans. Do you like French fries? Do you like? Let's get married. Or at least make some kids.
Oh,
at least
man.
make some babies.
I would hate to see what a frog chick baby looks like.
Probably similar to all the other animals that I make. They either have fingers or they don't. And they have one color or another. Nice.
So what happened in this situation was the chick scrutinized her environment by looking for a specific situation. The specific situation being, I want to have a blue frog that likes French fries. And when she found what she was looking for,
I know what I want.
That changed the process flow, because that influenced her decision to get married. If she did not find the blue frog that liked French fries, then that decision would not have been made, and then something else
history would have been
happened.
changed forever.
Exactly. Right.
All right, just to drive it in, let's go through one more example.
All right. I think there's actually two more. So here's the frog, and the frog has a task that wants to be carried out. Now, in this particular case, the frog knows that he has to add two numbers, but he himself can't add two numbers.
Nor does he know who can.
Right. So he has to scrutinize the environment to find an object that can. So he goes to the chick and he asks, can you add two numbers? So now he's not asking, are you this type of object? He's asking, do you contain this type of functionality?
Right.
Which is very important because both of those are very reflective concepts, and they're used very much in a lot of higher level
languages.
languages.
Pretty awesome, huh?
That's really cool. So can you add two numbers? And the chick says, no, I'm sorry, I can't. And then
really?
It goes,
that chick's
I know. Well, she wanted to marry a frog just because he was blue and liked fries. Right? There can't be too much going on upstairs there.
And just look at her. I mean, she's like,
she looks a little crazy.
Me too.
She looks like she should be on the Jerry Springer show.
Yeah,
you know? So then the frog asks the fly, can you add two numbers? And the fly very enthusiastically says, yeah, I can.
We need to give the chick a shirt that says, like, spicy. Or like crispy.
Yeah, crispy.
Kentucky Fried.
Kentucky Fried. Okay, so the fly says yes, he can. So now that the frog is aware that he has located an object instance that can perform the specific task he wants, then he requests to perform the task. And in this case, he asks, what is 5 plus 5? And the fly responds with 10. So Brian, just as a recap, what happened here?
So the frog knew that he needed to perform some type of action. Mm-hmm. And, like, maybe he even knew, like, the method name, for example. Who knows? So he scanned each object instance and asked to see if they contained a certain type of functionality. In this case, how to add two numbers. And so he looked, and then when he found one that could add those two numbers, then he just asked him to do the work. And if he wouldn't have found anybody, he would have just been like, sorry, nobody can add the numbers.
So, Brian, here's another one that's kind of interesting.
Okay. So now we have some sort of object. Some undetermined object that wants to know what time it is. It asks the frog, and then the frog asks, do you know what time it is? No, man, I just had numbers. I don't fucking know about time, man. Are you talking about time? Killing my buzz. Do you know what time it is?
Killing my buzz.
Yeah, it's time to eat French fries.
Nice.
So what is the time? I'm not sure. Oh, yeah, 10:15:23. So now he knows, and then he reports back to the object that asked.
Yeah.
So he was kind of he kind of staged himself in a reflective sort of a way as like a manager of the objects So he was kind of like he's like the office manager of the objects,
Now this is another important reflective concept, because in the first example with the frog and the chick and the fly, the frog had a task that he knew. It was coded in him. He knew that he wanted to add 2 numbers. In this specific example, a task was given to him that he did not know, for lack of a better way to explain it, at compile time.
Right. Ahead of time, he didn't know what was going to be asked of him. Some object just asked him a question.
Exactly. So that was not something he was predetermined to know.
Yes.
But he was fluent enough to figure out how to do it.
Yep.
So the frog had a task that needed doing, and the task was handed down, and he did not know this ahead of time. This dynamic task was asked of another instance to do, and then once he found the instance that could perform it, that happened, he got the response, and then he responded back to the calling code. Now there's one other example here, Brian, and maybe I can just kind of pose this as a what if. So like, what if the frog didn't ask the fly first? Do you know what time it is? What if he just said, tell me the time? What would happen? So
bad things might happen.
Let's see what happened. Let's start this over again.
Okay.
Make the assumption that the fly knows what time it is.
But that the fly doesn't. We're assuming the fly does, but he doesn't.
Precisely.
Right. What time is it? What time is it?
So, wait, go back real quick.
Yep.
Before he asked, he said, do you know what time it is? No, go to the frog. Okay. The last example, he said, do you know what time it is?
Right. And now he's just saying, what time is it? Right. Exactly. He's not asking him if he knows how to tell time.
Right.
He's asking him for the time.
Exactly.
I don't know, man. I told you before. I just fucking add numbers. Get off my back, man.
Boom!
Bad things happen.
Horrible, terrible things.
Terrible things. Terrible. You're all gonna lose your jobs.
Nice.
So in more loose implementations of reflection, object instances, classes, methods are assumed, and when that happens, if they don't exist, you're in trouble.
Yeah.
So the safer and way slower
way slower
is to go through and prestigiously check every single object to see can you do this? Can you do that? Okay, you can. All right, give it back, and I'm going to come back. Oh, he wasn't able to. Let's do mitigative action, blah, 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 blah. So, and it gets really slow, and that's one of the serious pain points of using reflection.
Yeah.
Among others.
And that's also why there's a decent amount of shops that are combing through code to remove reflection out of them.
Yep.
But it's still rampant enough to at least mention.
Yeah. And sometimes it's useful, so.
Yeah.
But we'll talk about that later.
So with reflective programming, you can also initiate instances without directly specifying the type. You can kind of look at this as, which we haven't really discussed code, but if I was going to create an object that was supportable by the environment, I can create an object of type object, assign it to a variable named myObject, and make that equal new object. Now you'll know what this means later on, but this is just pseudocode. Now in a reflective view, now this is just a mock-up, this isn't a real language, I can make an object type instance, but instead of making a new object instance, I can call some form of functionality that will take in a different representation, like a string, for example, of the name of that object.
During runtime.
Yes, and that could be dynamic. It could be a parameter pass, and then when that comes in, what it will do is it will check my environment. If I ask Brian, give me an instance of a beard. Well, you obviously know what a beard is because you have one on your face, so you can make one. No, bad one?
That's awesome.
I thought that was
that's cool.
Kind of funny, maybe.
Okay, so here we have our runtime has known object types. We have a chick, a fly, and a frog, and these are object types we know of. And the object's like, I need a fly, man. And then, that's an object type that we know about, so we can get you, we can hook you up, man. We got a fly right here.
Wait, is this a drug transaction or what? What's happening here?
So the frog's like, I'll hook you up, man. Here's your fly. He's like, awesome, thanks. See ya. Go put it in soup somewhere.
So the concept sounds pretty simple, right? And is it really that simple in practice, Brian?
Yeah, no, I don't know. Depends who does it. If some asshole puts it in there just because he's cool, then it sucks. But there's times and places for it, I guess. So I hope that that slams home the idea of reflection, and you'll probably see it in later languages. So I hope you enjoyed that.
Matter of fact, I can promise they'll see it in later languages.
That's true. Welcome to Designing Classes. So now we've walked through a lot of the concept of object-oriented programming. Now we're ready to really take a look at some of the best practices in designing classes and how that's done.
Yeah, because when you become a professional, if that's what you're aiming to be, you're going to see some horrific examples that are just not only confusing, but don't even make sense why somebody would even conceive this. So there are some things that Brian and I believe can be done to help make things a lot more simpler in the world of OOP.
A lot more simpler.
Yes. So, warning! The opinions expressed in this are not representative of the Whippet.net website. Viewer discretion is advised. So, basically what Brian and I are going to say, not everyone's going to agree with. I know some of you guys that are going to watch this are going to say, Kevin and Brian are stupid. Whippet.net is crap.
And hey, if you strongly disagree, maybe that disagreement will help you articulate how your best practice looks. Put thought in your class designs. It will save you so much time later, and it will allow somebody else who's picking up on your code or extending on code that you've written. It'll just make their day.
Yep.
You know, it'll make everything smooth. You'll reduce the chances of bugs. It's good. It's good for everybody. Some of the things we're going to look at is the fact that fields and methods should be named in a way that's easy for others to understand their functionality. It's not all about you.
Right.
You will not always be the only person looking at code. That's just how it is. And even if you are the only person looking at code, your past self is totally different than your current self.
Oh, you are so right about that.
So you'll come back to your code after you haven't seen it in a year and you'll be like, who wrote this? I wrote this? Really? What the hell is this? So make it easy on your future self.
Yes.
You know, just like David Bowie did, you know?
Think about the future, baby. In space.
So it's not always about yourself. It's also about your other personalities.
So also, you know, like if you have if you want to get the title of a button, you know, have it button.text. Don't have it button.attributed title text.
Right.
Just make it simple.
Also, not just fields and methods, but methods or actions should be spread apart to avoid making a single-purpose ecosystem. So you don't have a whole bunch of methods or actions that keep reinventing the wheel that do like slightly other specific things. So keep it abstract, keep it broad, keep it reusable. Yeah. That's really what this is about, is a lot of reusable code so that we can keep moving in these broad strokes and building on layers and building on foundations and making functional ecosystems of our code.
Why is this important? Well, Brian expressed some of these just a second ago, but consistency. Your future self and your past self are different people, even if it's just 3 or 4 months. So make sure that you do something that you know you will abide by later on. Also, for simpler implementation. Now, when we talk about simpler implementation, we mean that all of your different classes have very similar structures. So when you pull in one of the classes that you've written, you don't have to sit there and scratch your head for 5 minutes to know, oh, no, wait a second. What is attributed text title? No, wait, text, no, wait, how do I get the text on that? I better look at the code. You don't want to do that.
Right. For example, let's say you have a tree view object and you want to add a node to the tree view object. You'd say treeview.add, right?
Yeah, right.
Well, then it would make sense if you have a data grid view object. Surely you would also have an add method on it to add something to it. You would think, wouldn't you?
Hopefully. Yeah. Gosh, I hope so. It's also easier to integrate with other classes. So with the inheritance and that kind of thing, or if you're doing stuff like delegation, or if you just have 2 different classes where you want to use templates, where you're not specifying any data types, that's also very important for you to keep all that in mind. It's also easier for other developers to use your code and not have to reference documentation or read the source code.
Yeah.
I can't tell you how many times Brian and I at work or something have been forced to use some API that we, you know, whether we wanted to or not, we just use this API and we're just like, this doesn't make sense. Why did all these things just, it's like someone just threw up and sold it to you for $9,000.
And sometimes you have to inherit a project where it's obvious that 10 different people with completely different views of things had worked on it. It's horrible. It also slightly makes an easier process of polymorphism.
Yep.
A little bit.
Very much so.
So let's look at some naming methods. A good practice of naming methods is to use camel case. Camel case is a very simple way of expressing multiple words in one name. If we were to just say my method all lowercase, you'd be looking through it like, oh, this is my method, okay. But if we camel case the beginning of method, or camel case both my and method, it shows some sort of differentiation between the words to make it easier and faster to read.
So you can read that, because you're absolutely right. If my super awesome method was written all lowercase or all uppercase, you would not intuitively know what that said.
It would take unnecessary strain of your brain to parse that out. But now that it's camel case, we can just intuitively see this is my super awesome method.
Yeah. So also try to avoid using underscores for public members. It's a fairly common practice for developers to use underscores when using private members. Now again, this is not followed by everybody. But it does help the user differentiate the difference. If you were to inherit a class and you inherited a protected member, you would know that if it had an underscore that it was protected without actually having to read the code to know that it was protected.
Nice. Let's take a look at naming methods. When naming a method, we want to obviously use a consistent naming convention, but we want to show it in terms of an action description and then the field. When we can. So let's take a look at some of these examples. We can kind of split each of these into two halves. The first half is the action, like set, get, calculate, read, write. It's the action that we're performing. And then the second half will be the element that we're performing it on.
Mm-hmm.
So instead of saying like first name, get something, whatever, we can just say right away, I want to. It makes it a more natural language.
Yes, and
just like the way we'd speak this, we want to say, I want to set the first name. I want to get the first name.
And also the reason why keeping them in this context or in this convention for alphabetic purposes, if you're using something like IntelliSense, if you do instance dot set, you can see everything instantly that you can set right there. Because if you do first name set, well, if you do F, not all the set methods are grouped there. Right. So that's why it's so great if a method is doing an action, like setting, getting, calculate, make that action the first word.
Beautiful. Now let's look at naming attributes. So global fields, generally speaking, will start with an underscore.
Or they should.
They should.
It's good practice.
Yes. That way, anytime you see that underscore something, you know that this is global. You don't have to go looking through the source code, figuring out, is this globally defined? Was this defined in some other weird freaky scope, something? Yep. You know right away, as soon as you see that underscore, whatever, it starts with an underscore. It's globally defined. Now, global fields can be constants and they cannot be constants. A lot of times, if it's all uppercase, that tends to indicate that it's a constant global. And if it's camel case, that tends to imply that it's non-constant. It's variable.
Mm-hmm.
Local variable properties use similar conventions as methods.
Right. Because you don't want your properties to have underscores.
Right.
Because properties are always publicly available.
Yep. And use properties to access private global fields if you're using a language where properties are supported. Sometimes you'll see that properties versus variables will begin with an uppercase in the camel case, and local variables will begin with a lowercase, but they'll both be camel case.
So, when defining methods, make the actions of an object relevant to all instances. Now, when I say this has to do with inheritance. So if I'm going to make a car or some sort of an engine type thing, every single type of car that exists will start, it will stop, it will accelerate, and it will brake. And the reason why that's important is, like, let's just say I want to make this type of car, or I want to make a truck that inherits the properties of a car but just changes it a little bit. The methods that I have defined in car are directly applicable to every single type of car or every single type of object that inherits from the car. So you also want to design as modular as possible. And the reason why you want to do that is because it's always good to keep things that are being reused in different areas separate. So if you have something that, I don't know, when you start a car, you access the engine or something, let's just say as an example, that accessing of the engine should be something shared. So that if you have to change it, you change it in one spot. You don't change it in every single spot that accesses the engine, if that makes sense.
Right, regardless if it's a car or a truck or a tank or an airplane or whatever it is.
Exactly, right.
That start engine method stays intact.
Mm-hmm.
But then that also speaks back to the idea of thinking in abstract terms. And that's kind of one of the things that you want to do is you start looking in objects in the real world in terms of object-oriented programming and start trying to train your mind to think in these broad abstract terms. What do things have in common? What do things not have in common? What did an object inherit from something else? Yes. And just really train your brain to think in those terms so it's natural. Design internal methods as modular as possible to maximize reusability.
Brian, what do we not do?
There's a lot of examples out there where you're going to see somebody make reference to something like this, where they define a method like there's a car object and that object has something like drive to work. Right. That's such an absurdly specific method name. Why would you do that? That's just bad.
Wrong.
Bad.
Wrong.
That's not abstract. Like, it's not going to be reusable for a lot of other things. What if you want to drive to a grocery store? Now you got to write a whole other method. That's stupid. So driving to work is not an action of every single car that exists.
Yeah.
Not everybody's going to drive. You might be an Upper East Side house mom from New York City.
Yeah.
And they're not going to be driving to work ever because they don't work.
Or maybe you drive your motorcycle to work and your car you don't drive to work. Or you drive your bike to work and not your car.
So the action should be more generic.
Yeah, absolutely.
So here's a better way to do it.
Yeah. So a better way to do it would be to say drive to location, and we could pass the latitude and longitude of the location that we want to drive to.
So that way, no matter where we're driving to, if we want to drive to work, it would take almost no additional effort to simply pass in the latitude and longitude of where work is.
Right.
It keeps it flexible, it keeps it abstract, it keeps
it
usable.
Right, and this method can be reused for any location that we want to drive to. So a car will always drive somewhere, and of course, unless it's, you're Jeff Foxworthy and it's on center blocks in your front yard and you cut your grass and realize, oh, I have a car. Wow. So this method is a lot more generic. It can be used to drive to work. You can go to the mall. If you play a sport, like you had, your kid plays football, take them to practice, whatever. This will let you do multiple things with the same method. Although this is better than drive to work, in this case, it's technically not practical because the car doesn't drive itself.
That's true.
but it's still better. So if you really, really, really want a drive to work method, I need to have this, Brian. What do you do?
If you really need it, you can inherit the object and you can extend it to being my car of a particular, this is my car that does this function. It drives to work.
Yep.
But that's calling it not a car abstractly. It's calling it, my car. And all of my cars will drive to the same work location.
Exactly right. What else should we not do as far as naming our methods, Brian?
So here's a strange case, camel casing. And this is not camel casing. This is PDF odd pages _ retrieve. I mean, what is that? Seriously.
Did you actually pull that from somewhere?
No.
Oh, okay.
But people do the. I mean, that looks like
that
something,
looks like something I've seen before.
Especially some of those supportive PDF libraries like PDF Sharp. That one's not that bad. No offense to PDF Sharp. iText Sharp's good.
Yeah, pretty good.
But some of those other ones, not iText Sharp, have kind of really stupid method names. A better one would be get pages PDF.
Right, yeah.
And then we pass it some enumerated value like odd. So now we just want the odd pages. And if we don't pass it a value, it gets all the pages. So
right. Or it can be overloaded so that you can pass an integer for a certain page or an array of pages.
Right.
Or maybe a string that lets you do 1-4, so it's pages 1 through 4.
Right. But in the bad example, it's just saying only retrieve odd pages.
Yep.
For PDF, it's dumb. Or if it's a chess game, for example, move _ rook destination. Now you have to write a different method for every single different type of chess piece.
Yeah, so now let's just say that even though chess is 1 billion years old and it's never changed, what if a new piece is added? You have to update every single piece of software that exists to accommodate for that.
Well, and the other thing too is this just moving it, or is it, what we're really doing when we say move a rook, because we need to be able to undo, need to be able to keep track of the stuff. We're really going to be adding that move into a list of moves that have happened as we kind of build that tree of chess as we play the game. So move _ rook really isn't explaining properly what we're doing. What we're really doing is we're adding a move.
Yeah, right.
We're adding a move and we're passing, for example, an enumerated value of the rook of that type of chess piece, and then we'll pass it the destination of where we're moving it to. And that can, return true or false if it was a valid move, whatever. Also, more generically, item.value might not be as good as something like item.getCost.
Now that's a little controversial, but I see what you mean by that, because the dot value is great when defining a generic object type, but if something like NSObject has those generic return types, but if you do inherit from that object and it's something like an item, you're at a store that has a cost, getCost is more it explains more of what you're getting.
So that's kind of a case where you kind of go too oversimplified in the other direction.
So guys, the best practices in OOP design. Number 1, use inheritance. So let's just say, for example, Brian, you and I are Whippet.net Incorporated, right? And we want to write the greatest Office suite ever. So we'll basically take the source code from OpenOffice, change one line, and recompile it and say it's ours. Okay?
Right.
So let's just say if we wanted to do that from scratch, what we would do is we would define a single class that encompasses all the similarities of a word processor document, of a spreadsheet document, and a presentation document. And then when we want to create each individual class, we will inherit from this parent class that contains all the basic functionality.
Right, so we'd have a document class, which would be the superclass.
And the reason why we want to do that is because any of the other external functions and methods that we embed in other classes, we don't want to specify the data type that's coming in. We also want to be able to use the same common methods to do stuff. Like I want to print an I'm going to print a calc wedge spreadsheet. I want to print a writer document. Those two, I should not have to like specifically say, well, if this is this type, here's the print method. If it's this type, here's the print method.
Right.
I should say print on all of them and it will just work.
Also, make sure to build your methods to be as modular as possible. Obviously without going insane.
Yeah, because you can really go crazy doing this.
So within reason, where it's useful.
The basic concept of modularity is reusability. If you're making a function or a method that could potentially be reused, make sure you keep that in mind. If it's something that is a single purpose, then modularity is not that important.
And also, the modularity and reusability really boils down to the idea of less lines of code.
Yeah, absolutely.
So, if being more modular creates a circumstance where you result in more lines of code than being less modular, then that's too excessive. Also, build your ecosystem with as much abstraction as possible.
Oh, yes. Very important. Don't make it complicated for the programmer using your code. So make sure that your methods do everything and that the person interacting with your code only has to know how to use it and not what it does.
But also has the most flexibility possible. Designing complicated code on purpose does not solidify job security.
People don't get this.
And it doesn't make you cool because for some reason, and I've seen too many of these cases where you have these people who act very intelligent and like you ask them a question and their hand and their eye twitches and they solve a Rubik's Cube, but their code is way over-engineered. It's grossly over-engineered. The most intelligent programmers are the most elegant programmers.
Yep.
You know, you're not going to find John Carmack's code 5 billion lines long. He's going to figure out a way to use some freaky constant and cut down those 10,000 lines into 15.
Right.
And that makes a more intelligent, elegant programmer.
And that's how he is a great programmer to look up to because he could on a watch write the most amazing graphics engine you've ever seen using that small amount of resources. And really when you look at it, when you have less lines of code, when your program compiles, you are literally giving the computer less instructions to perform. Remember now, when you start looking at things like the Hertz rate on a computer, that's instructions. The more instructions that you perform on a given interval, the longer it takes, the more resources you consume. So that whole idea of having less lines of code is directly linked to how fast your program will execute. Is that right?
Yeah.
Okay.
Well, depending on like loop structures and stuff, but
yeah,
whatever. When actions could have multiple results, allow for delegation.
Yep.
That way you can customize events and the process to fit the needs of the program without having to redefine every event handle every single time.
Yeah, I mean, it's not a bad practice to have a default action, but allow it to be overridden by some sort of a delegate. Also, use properties to access private and or protected fields externally. We've discussed this before.
And so, I mean, this list probably kind of feels like a summary review of all the concepts we've been going over in the series. And that's basically what it is. So, just like we talked about with namespaces, take advantage to categorize your class.
Oh, yeah. Right.
Especially when it's a very large project. And also, when we talked about constructors and destructors, use those destructors to keep your memory clean. There's a few things that are more annoying than using compiled library that just leaks memory somewhere deep in the code.
Because
you have to just go fishing and rooting.
But even at that, if it's compiled code, you're can't screwed. Actually access it.
Right.
What you have to do in those circumstances is design your program so that it doesn't run, so it has short executions.
Right.
So a process calls this process and kills itself. Because if you have a memory leak deep inside some library that you can't change, you're stuck. You can't run it.
Yeah.
And you may be forced to use that library contractually or something,
So keep your ring clean.
Yeah.
So build generically to maximize, class usability and reusability. And give member names that are relevant to what they do. Don't call something button click 1. Just take the time to name it.
Yeah.
Take pride in your code. If you're just being sloppy about it and you're just rushing, the amount, you think you're saving time sometimes with that just by like naming things whatever and moving along. It will cost you, I guarantee it will cost you more time down the road.
Absolutely. The more logical and modular your classes are designed, the more usable they will end up being.
And whatever programmer philosophy you choose, try to stay as consistent to it as possible.
Yes. Wow, we did a pretty decent job summing that up.
Yeah.
So we've gone over in this video series some extremely, I think, very valuable information.
Yeah. And what some people would consider very advanced concepts, which really aren't once you boil them down and take a look at them.
My goodness. Like,
if people would just stop acting like cool and acting like they have, like a private access to, you have to go through their public getters to information that nobody else can, whatever.
They don't have any friendly functions.
Hoarding information does not give you job security. It's like we talked about in the very first video when we said, am I a software developer? Like these concepts and these things that you learn, learn them so that you can express them to other people. That will just that will make your team stronger, that will make the programming community stronger. And when the development community is stronger, there's more technologies that arise that you can benefit from and develop off of and, profit on maybe. So.
Okay, cool. Well, thanks for taking this journey, guys. We'll pick up with you guys again in C++.
Yep.